This is lecture 24, and today we're going to finish the part about geostatistics. So the last lecture we covered simple kriging. Simple kriging is an interpolation method. Well, we look at different kriging methods, but we focused on simple kriging mostly. So we discussed the simple kriging interpolation. So we want to estimate, so the problem, we're dealing with an interpolation problem where we have a bunch of sparse measurements and we want to estimate the value of the property at a given location, which was not sampled. So in the simple kriging, we assume that the mean is constant and known. Then what we do is that we take the simple kriging estimate equal to the mean plus the sum for I that go from 1 to n of the weights times the value of the measurements minus the mean, where Wi are solved as a system of equations. I guess I only written it for the specific case, or n equal 3, so I'm going to do it for the general case here. But this is pretty simple to extrapolate. This is C11, this is C1n, this is Cn1, this is Cnn, not the TV show, the TV channel. And then this is W1, Wn. Remember that you have as many weights as the number of measurements. And this is C01, C0n, where 0 is the subscript that indicates the location of the point where we want to make the estimate. So in ordinary kriging, we have essentially the same equation, but now we use a local mean that is computed just using the point in the neighborhood. Okay, so now what happens if we have direct measurements of the properties of interest and some indirect measurements? So the problem that we're going to face today, I want to highlight that this is an interpolation method, because later on we're going to see some methods that involve stochastic sampling. So I'm going to try to explain the difference later on. Now, but before doing that, I would like to consider the case where we have, say, xi direct measurements. So when I say direct, it means that I misspelled measurements. When I say direct, I mean that these are measurements of the property that we care about, just at different locations. Okay. So for example, you want to estimate porosity here, and you get one measurement here, one measurement here, and one measurement here. X1, X2, X3 are measurements of porosity, which is the property that we're interested in, just at different locations. But then on top of that, we have Xj that are indirect measurements. So this means that this is not the property that we care about. So for example, X could be porosity, and Z could be the velocity. But somehow velocity and porosity are related to each other, for example, using a linear relationship, like one of the rock physics models that we studied, or just a linear correlation, or some kind of complicated rock physics model. So here you can have as many as you want. And generally, the direct measurements are actually limited in number. So typically we have more indirect measurements than direct measurements. But the method can be applied anyhow. So let's say that, for example, here we have some measurements of velocity, Z1, Z2, Z3, and Z4. Now, this is a typical case for geosciences. For example, in reservoir characterization or in general in subsurface characterization or modeling. You have a lot of indirect measurements that are on a regular grid because these are things that are measured at the surface. So you can design your geometry such that you acquire, for example, seismic velocities every 25 meters in each direction, or resistivity every 10 meters in the along a 2D line, and so on and so forth. And then you have a bunch of direct measurements, which might be the boreholes, the measurements at the boreholes or core samples or so on and so forth. So a typical situation is something like this. We define a regular grid. Well, let's just represent the nodes. So you have some locations along a regular grid where you have measurements of the secondary property. So I forgot to mention, I like to call them direct and indirect measurements, but the common terminology in geostatistics is primary and secondary variable, where primary is the one that you are interested in and secondary is somehow related to it. So this one here is the secondary variable. And this one here is the primary variable. So now the secondary variable can be measured along a regular grid, and then say that we have maybe 3 boreholes, like in the previous case, where we have some direct measurement of the primary variable. And now let's say that, for example, you're studying an aquifer or a reservoir. You want to drill at this location here because you got the permit, and you would like to estimate the property, for example, porosity or water saturation. So if we don't include the secondary variable, it's exactly the previous case. So if we do the simple kriging, here we would get that xk is equal to the mean of x plus the sum for I that goes from 1 to 3 of wi, we know how to compute those now, of xi times xi minus mx. Now, we want to account for the secondary variable now. So what we're going to do is simple co-kriging estimate. So in the simple co-kriging, essentially we have the first step is exactly the same. I'm going to call it ck. So we have mx plus the sum for I that goes from 1 to, in our case it would be 3, but let's make it general to n, wi times xi minus mx. Now we have to deal with the secondary property. Well, we're going to do exactly the same. We're going to sum I that goes from j to m of vj, that we have weights that we have to determine, xj minus mz. So now I'm going to clarify what these terms are. So wi and vj are the weights. xi are the measurements of the primary variable, so the primary data. zj are the secondary data, or the secondary variable measurements. mx is the mean of the primary data, and mz is the mean of the secondary data. And then n is the number of primary measurements of the measurements of the primary variable, and m is the number of the measurements of the secondary variable. So again, this is a typical case where you have, for example, seismic data or electromagnetic data. So the green property could be Vp, or it could be resistivity, and then the primary property could be porosity, water saturation, and so on and so forth. It's impossible to measure porosity and water saturation at all the green locations, but we can measure VP and resistivity that are related to porosity and water saturation. Okay, now this is the simple co-kriging is actually pretty complicated to do, but despite the name simple. And the reason is that, so in order to compute Wi and Vj, we need the covariance function of the primary variable. I'm going to call it Cx of h. So this is the covariance function of the primary variable. Cz of h, which is the covariance function of the secondary variable. And then we also need the covariance function of x and z, which is generally called the cross covariance. So this one here accounts for how the correlation between x and z changes as a function of space. So you would have a pretty complicated system where here you have Cx, here you have Cz, and Cz is generally much bigger than Cx. We can measure more secondary properties than primary. We can measure the secondary property at more locations than the primary property. And then here you have the weights W1, Wn, V1, Vm. And then here we have the usual C01, C0. This would be N plus M. So this is pretty complicated to do. And it can be computationally demanding. Because, for example, if you have seismic data, you might have a measurement every 25 meters. Again, solving the system is not that complicated, but assembling this matrix here might be complicated. So in most of the applications, we don't do the full co-kriging. What we do is the so-called simple collocated co-kriging estimate. So collocated means that we are actually studying the secondary property that is the closest to the location where we want to make the estimate. So I'm going to try to reproduce this graph here. So what we do is we only use one data point for the secondary variable. Now, collocated suggests that it is the one that is at the same location where we want to estimate the primary variable. Now, it might not be available, so we might have to pick the closest one. But in general, so you have all your data points in the background. I'm not going to plot all of, well, I don't want it to be confusing, so I'm going to do it. Guess I skipped one here. Now, what we're going to do is if the location is here, so this is where we want to compute our estimate, we still need our three values of the primary variable, but we're only going to account for this point here for the secondary property. So we don't have a sum anymore, like here. We just have one point. So we only have to estimate one additional weight. So the system, the estimate is, I'm going to call it CCC, collocated co-kriging, is mx plus the sum for I that goes from 1 to n of wi times xi minus mx, and then we have one weight, which I call v, times z, I'm going to call it z0. It's this data point here. So it's the value of the, it's the collocated secondary data, the value of the secondary property that is the closest to the location where we want to compute the estimate, minus the mean. So Z0 is the collocated secondary data point. Now the system becomes smaller. So here we have C11, C33 in our case. Let me do it this way. I'm going to explain it in a minute. So I'm going to write it for n equal 3 and m equal 1, essentially. This is C12, C13, C23, C21. Well, it's symmetric, so it doesn't really matter. So it's C31, C32. Okay. And this is for the variable x. So I'm going to write an x here, just to make it clear. And then here I'm going to have C x z cxz. I'm just going to call it 1, 2, and 3 because I know that I only have one data point for z. Well, if we assume that we could also call it, if you want, C01. Because we assume that the location of Z0 is very close to the location of X. And then here this would be C of Z. And then it's C, this is symmetric. Okay, and then here you have the weights W1, W2, W3, and V. And then here you would have CX01, CX02, CX03, and then here you have CXZ. Well, this is it would be 0, 0, so I can just call it CXZ. Okay, well, this quantity here can be replaced with the variances of X. And this one here is the variance of Z. Now, generally, we assume that the cross covariance CXZ is hard to estimate because generally you don't have enough data. So we generally assume that CXZ of H is equal to the variance of Z divided by the variance of X times the correlation between x and z times the covariance of x. And so essentially, the input, if you want to implement it, are simply the variance of x, the variance of z, and the correlation between x and z. This one here is generally called the Markov assumption. Anyway, so this is very similar to solving a Kriging system. Now, most likely you're not going to have to implement these details, but this is very similar to the Kriging system, except that now you have this additional term. This is just a scalar, so V is one weight, Z0 is one measurement, and MZ is the mean. So it's exactly the same system as before, but now you have an additional column and an additional row. And the first part is exactly the same. So this would be the same covariance matrix that we have used in the past for the simple Kriging. But now you have this additional weight, you have a cross correlation here and here on this row and this column. But if you use the Markov assumption, you can compute the cross correlation by simply applying this equation here. Okay, now we switch to a different geostatistical topic, which is called geostatistical simulations. So let me briefly introduce the topic this way. No matter which kind of strategy you use, simple Kriging, ordinary Kriging, Kriging with locally variable mean, collocated co-Kriging, if I give you 3 data points and maybe a bunch of values for the secondary property, I'm going to give you like 6 just as an example. And now I ask you to compute a property here. Okay. Well, if I do it 100 times, I'm going to get always the same solution, right? So this is an interpolation problem. So you can use simple Kriging. You can use ordinary Kriging. You can use whatever you want. Well, these methods will give you different answers, but in general, if you apply simple Kriging 20 times, you will always get the same solution. There's nothing, unless you change your variogram or you change some of your assumptions. But there's nothing stochastic, there's nothing random in this. The interpolation itself is deterministic. The geostatistics part is that we assume a spatial correlation model. But we're not sampling, we're not adding any stochastic component. So this is an interpolation problem. Now we're going to switch to a sampling problem. So the scenario is essentially the same. You have your tree measurement, you might have some measurements in the background. And now you want to estimate the value of this property here. Now, what I would like to do, instead of estimating the property, I want to estimate the PDF or the probability of x bar given, for example, xi and maybe zj. And then once I get this probability, which might look something like this if it is Gaussian, I want to sample from the distribution. Sorry, this is mu x. I want to sample from the distribution. And for example, if I sample one time, I'm going to get this value here. So this might be my first sample. And then maybe I sample another time, and I'm going to get a value here, and then again a value here. So with the sampling method, if I repeat it 100 times, I'm going to get 100 different solutions. Now, the reason we do it is that the interpolation method minimizes the least squares. So we often say that kriging is the best interpolation method, best in the sense that it minimizes the least squares. You cannot do better than that. Now, when we sample, we generate multiple solutions. We call them realizations. And these ones here, they're supposed to represent the heterogeneity of the property and the uncertainty in the property, or the variability of the property. So the goal here is to, above, it was to get the estimate that minimizes the least square error. And then here we want to represent the uncertainty or the heterogeneity. Okay, so how are we going to do it? Because I told you in the previous lecture that the trick is that if I want to do it at two different locations, for example, one here and one here, I cannot do it independently because these two values, they have to be somehow correlated, because there's a spatial correlation model that is supposed to represent the continuity in the geology. So the challenge here is sample to sample with spatial correlation. And in geoscience problems, the idea is to mimic the geological continuity. So the most common approach is called sequential simulation. And the idea is relatively simple. Let's say that you have a spatial model, and excuse me, we're going to divide these models in different cells. Okay, something like that. So let's say that at some locations we have a measurement. So here it might be x1, x2, and x3. So these are the locations where we have some direct measurements. And for now, let's assume that we don't have a secondary variable, but we are going to include that. So the idea is that we randomly visit a location in space, a location, let's call it K, in the model space. So for example, we could pick this one here. So this is K equal 1. Now at location K, we draw a value from a PDF of the property of interest. And we will have to discuss how we determine this PDF, define this PDF. So this is the random sampling component of the method. Then we move to the next location. K plus 1. And we do exactly the same, but we use the previously simulated values to condition the new simulation. So at location K plus 1, which is selected randomly as well. So we might go here, for example. No. So we might go here, and this would be K equal 2. So we go from here to here, and then we might go from here to here, and so on and so forth. So at the location K plus 1, we use the previously simulated values. At locations 1 to K, to condition the random sampling. I'm going to give you an example which should clarify how we do it. So in our graph here above, let's see if I can keep it in the same page. Well, I guess I can. So first we're going to start with location K equal 1. So we are going to define the PDF of X at location K equal 1. And this is going to be conditioned by the measurement, X1, X2, and X3. Now, we draw a random sample. We're going to call it XK1. And then we're going to move to the next location, K equal 2. Now here, we're going to define a PDF, which is the probability of XK equal 2, given X1, X2, X3, and XK1. So these three are the X1, X2, X3 are the three direct measurements. And then XK1 is the previously simulated value. Now we draw a sample, XK2. Now we move to location K equal 3, and we have the probability of XK equal 3 given by conditioned by X1, X2, X3, XK1, XK2. And we draw a sample from that, which we call XK3, and so on and so forth. And we keep doing it until we visited all the cells in the grid. So we're going to do it until we get K equal N, where N is the number of cells in the grid or in the model. So by doing that, when you reach the end, let's say that we visited all the cells. So at some point we get to K equal N. Well, let's not put it in the corner. Let's put it here in the middle. K equal N. Now we have already simulated all the values in the other cells. So n is the last one of the cells that we randomly visit. So now when we compute this PDF here, we're going to compute a PDF, which is the probability of x for k equal n, given x1, x2, x3, and then we have all the xk1, xk n minus 1. Now, since we are using all the points that we have simulated to condition the simulation at this location here, what happens is that the value has to be pretty similar to the values of the cells around it. So that's how we reconstruct the spatial continuity in the data. Now, this PDF here seems pretty complicated to estimate. So there are some methods where we can use the techniques that we already know to build this complicated PDF. The most common method is called sequential Gaussian simulation, and it directly uses the kriging. So I'm going to try to draw a simple grid, let's say 5 by 5, for example. Okay, let's say that we have some measurements, x1, x3, x2. So the first thing to do is to determine a random path that visits all the cells. So for example, we could start here. Instead of calling it xk1, xk2 to avoid confusion, I'm going to call it x4. But the first three, so this is the first location, like our step k equal 1. The first three are actually points that we have directly measured. So this could go x4 here, maybe x5 here, x6 here, and at some point we get location x7. Let's say that this is the one that we're trying to estimate. So we have already simulated x4, x5, and x6. So here we are going to do our steps. So we have the k is equal, so this is the fourth location in the random path. Well, if you want, you can just assume that 1, 2, and 3 are already simulated, so we can call this one here K4. It doesn't really matter. So let's say that we are at location K7, and we have already simulated. So x1, x2, and x3 are measured, so there's no point of simulating there. And then x4 and the x5 and x6 are simulated. Okay, so once we choose the location, we want to sample a value, but first of all, we have to build the PDF. So what we do is that we compute the kriging system, and here we need the kriging mean, or the kriging estimate, and the kriging variance. So the kriging estimate, let's say that we use simple kriging, but you can also use ordinary kriging if you want, at location k is going to be equal to m of x, the mean of x, plus the sum for I that goes from 1 to n of wi times xi minus, sorry, this one here, it goes to k minus 1. So in our case, 6. Because we have already simulated 6 values, or measured or simulated 6 values. and we detrend the data. And then we have the Kriging invariance, which is, well, I guess I can just use a bar instead of SK to simplify the notation a little bit. So this is going to be the variance of x minus the sum for I that goes from 1 to k minus 1 of wi times the covariances ki. Okay, now we build a Gaussian distribution. PDF, which has the mean equal to the Kriging mean and the variance equal to the Kriging variance. Now we draw a sample. So you can actually prove that this Gaussian distribution here is the probability of xk conditioned by x1, xk minus 1. We're not going to do it, but you could. So now we draw a sample. So xk is drawn from this Gaussian distribution here. And then we move to the next location. So xk now is a simulated value. And then we repeat the procedure until we visited all the cells. Now, let's say that, so from once we simulate x7, we're going to move to another location, which is going to be x8, and so on and so forth. So what we do here is simply we take this distribution, which is Gaussian. The mean is the simple Kriging estimate, and the variance is the Kriging variance. And then we draw a value, which we call xk, and it's the simulated value. And it can be anywhere according to the PDF. Now, what happens is that this method here is used to generate multiple realizations. So the acronym is SGS, or sometimes SGSIM, is used to generate multiple realizations. And the generation of multiple realizations is obtained by taking different random paths. So every time you follow a different random path in the grid, so you visit the cells in a different order, so this gives you the variability that you need. Well, I guess. Now, let's see what factors affect the... okay, despite the name sequential Gaussian simulation, this can be applied also to non-Gaussian distributions, because so if x or the PDF of x is not Gaussian, you can always do a normal score transformation. do the transformation in the, do the simulation in the normal score domains, which means essentially the quantiles, and then transform back. So essentially what happens is that if you take a distribution which is, for example, like this, you can actually apply a normal score transformation and make it Gaussian, do the transformation in this domain, and then transform back. This is something that the commercial tools that implemented sequential Gaussian simulation already has inside. So you provide an histogram of the target property, and if it is not Gaussian, the software does a normal score transformation for you. Now, in terms of input, you have to specify a prior distribution because you need the prior mean and the prior variance of x. But remember that at each, well, you also need the random path, of course. So the way generally people do it is that, like if you want to implement it in MATLAB, you assign a number to the cells. For example, 1, 2, 3, 4, and so on and so forth. And then you randomize the sequence, and then you visit the cells in that order. But remember that you have to solve a Kriging system or a Kriging interpolation to determine the mean and the variance. So you need to compute the weights, and the weights are a function of the correlation function or the covariance function. So you also need the covariance function or model. Now, if you choose a covariance which where the covariance drops down pretty quickly, then you're going to get a different model than if you choose a covariance that goes down pretty slowly. So in this case, this model is going to be pretty smooth, whereas in this case, the model is going to be pretty noisy. I'm going to send you a PDF attached to this lecture where I show you some examples of the impact of the spatial correlation. Now, you can also apply sequential Gaussian simulation with collocated co-Kriging. So now let's say that you have a secondary variable. These are generally called sequential Gaussian co-simulation or sequential Gaussian simulation with collocated co-Kriging. Well, the idea is exactly the same. It's pretty simple to generalize because instead of doing the Kriging step, you're going to do a co-Kriging step. But let's try to reproduce my graph. And again, I'm going to send you some notes where these graphs are much nicer. So we have exactly the same scenarios before. We measure some data points, x1, x2, and x3. And then we have already simulated some value, x4, x5, x6. So we want to simulate x7. But then we assume that at the location 7, we also get a measurement which is z7. And this is the same for the other locations that we have already visited. So now we are at location k equals 7. We do the co-Kriging. So xk is equal to mx plus the sum for I that goes from 1 to k minus 1 of wi. The first part is exactly the same as you have already learned. And then we add the coefficient v times the property at location k minus the mean of the secondary property. And then I guess I never gave you the equation for the variance, but I'm going to write it here. This is sigma x squared minus the sum for I that goes from 1 to k minus 1 of wi times cky. And then we have minus v times the cross correlation of x and z. So this one here is the correlation of the covariance function of x for assuming that the distance is equal to 0. And then we assume that a Gaussian distribution so this is the probability of x at location k given x1, xk minus 1, and zk. And then we draw a random sample, which we call xk, from this Gaussian distribution here. And then we repeat the procedure. So generally, when you do sequential Gaussian co-simulation with collocated co-Kriging, when you do this step here, since you have an additional conditioning variable, you reduce the uncertainty compared to the SGS, the standard SGS method. And the more secondary variables you have, the less uncertainty you're going to have because you're including more constraints. Now, one thing that I didn't tell you is that if you do, I'm going to write it as a note. Let's say that if you generate a large number of realizations, where we assume that n is large, what happens is that the mean of their realizations is exactly the same, is very close to the Kriging estimate. Generally, if you have 1,000 realizations for a 2D map, the mean is exactly the same as the Kriging estimate. Now, in practical applications, there are two ways to do it. So most of you are geologists, so you're going to build somehow models in the subsurface. So let's say that, for example, we want to build a 2D map of porosity, or even a 3D model. It doesn't have to be a map. You can do it in 2D or in 3D. And you have, let's say, 5 wells, and you have seismic velocities, a 2D map or a 3D model of seismic velocities. There are generally two ways to do it. Method number one is you solve an inverse problem, the rock physics inverse problem that you did in the homework. So we know that VP is equal to some kind of function of porosity. So you compute a 2D map of porosity, or again, this can be applied in 3D as well. a 3D volume or a 3D model. Now, this one here, Jenna, since we're talking about seismic velocities, this is a low resolution. So this can be used as a trend for sequential Gaussian simulation. I'm going to call them, use the seismic porosity. So the porosity derived by the seismic velocities in sequential Gaussian simulation with locally variable mean. So this means that the mean mx, so mx comes from, is a pointwise model that comes from, is the seismic porosities. So essentially you take your 2D map or volume of, or 3D volume of velocity, you compute as a solution of the inverse problem the porosity. This is going to be very smooth because of the features in the seismic velocity. So you can use it as a trend, almost as a background low frequency model to build sequential Gaussian simulations where the mean is computed from the seismic data. Otherwise, you can do sequential Gaussian simulation with collocated co-kriging. So essentially, you do exactly the previous step. Most of geophysicists would probably tend to do the first step, but the collocated co-kriging is relatively simple to do. And the collocated version is actually convenient in this case because the seismic velocities are very smooth because of the low resolution of the data. So the full kriging system wouldn't add any advantage in the process. So this means that we simply run the sequential simulation with m equal porosity and x equal porosity and z equal vp. And at each step we solve the collocated co-kriging where the velocities are used to, the correlation between porosity and velocity is used to compute the weights. Okay, the last part of the class, I want to cover a special case. What happens if instead of continuous properties like porosity, we have a discrete property. Now, this method here, so we have seen the kriging, which is for interpolation. And we have seen the sequential Gaussian simulation and the co-simulations as well, which is for sampling. So all these methods here, they're used for continuous properties. Again, the property doesn't have to be Gaussian because if it's not Gaussian, we can do normal score transformations like I pointed out earlier on. But at some point, we assume a Gaussian distribution, and this is true for a continuous property. So what happens if we have a discrete property? So an example of discrete property is the facies or the rock type. For example, what if we're interested in classifying sand and shale based on seismic velocities? Well, we essentially use a trick to apply the same methods that we have seen so far. So in the case of discrete properties, what we do is define what we call indicator variable. At each point. say k. So we define I of k, which is equal to 0 if the discrete property is observed, or let's say, I'm going to show you a more concrete example. So if k is shale and 1 if k is sand. So let's assume that we only have two properties. So we're going to work with rock types or facies, and we assume that we only have sand and shale. Now, the mean of the indicator variable is equal to the proportions of sand, which we call pi. And then the variance is equal to pi times 1 minus pi. You should remember this from the Bernoulli distribution. So by transforming the discrete property into the indicator variable and using the proportions, we can define the indicator kriging. So essentially it's exactly the same method, except that now we have to define, instead of defining the kriging estimate, we define the probability. So for example, here we have the probability of the indicator kriging at location k. This is going to be pi plus the sum of the weights of wi times xi, the indicator, I k. Oops. Well, I guess let's call it j. Otherwise, the notation is silly. Minus pi. And then this would be for the sand. So the one for the shale would be 1 minus the probability of the sand. And this one here is exactly the conditional probability that we need. So the indicator kriging probability is actually the probability of the indicator variable at location k be equal to 1, given the values of the indicator variables in the previous locations. And based on that, we can define the sequential indicator simulation. So it's exactly the same process as before. We selected location k randomly according to a random path. We compute the local PDF, which is the probability of that we computed with the indicator kriging. Which is the conditional probability of the indicator being equal to 1, given the previously simulated values. And then we draw a sample, which is either 0, 1. So typically we draw, the way to do it is you draw a uniform, a random number uniformly distributed between 0 and 1. If it is greater than pik, then this is equal 1. And if it is less than pik, this is equal 0. And then you repeat the procedure. Now, sequential indicator simulation and indicator kriging are not often used in geosciences. There are some more advanced methods that somehow replaced these methods here. For continuous properties, the sequential Gaussian simulation and the kriging are still commonly used, but for the discrete properties, it's more common to use more advanced methods. The problem is that you can only account for the correlation between two properties, between the same property at two different locations. So there are some methods that accounts for the correlation between properties at multiple locations. The most common method is called multiple point geostatistics. These methods here, and then there's also object modeling. These methods here are not do not have a closed form, so they cannot be expressed with equations. These are more computer science algorithms. But the idea of multi-point geostatistics is that you basically take a conceptual model and you try to extract all the statistics that you need from this conceptual model. These conceptual models are called training images. We're not going to look at those, but just in case you hear multi-point geostatistics, it's an advanced method in geostatistics that accounts for higher order statistics in the data. But you need to have a much larger data set. So what people do is they take conceptual models and try to extract statistics from those. For example, if you want to model a channel reservoirs, you take an image of, like a cartoon of a channel reservoirs, and you try to extract the statistics from there. These methods here, they are more realistic, but so the advantage here is that these methods are more realistic, but they're harder to condition with secondary variable. Or more difficult to condition. Okay, that's about it. That's probably all I know about geostatistics. So in the homework, there's going to be a problem where I'm going to ask you to solve a simple kriging system using some measurements. It might be a little bit long, but it should be pretty simple, because essentially the only thing that you have to do is really apply this equation here. I'm going to provide all the inputs, so it should be pretty straightforward.